Hello, everyone. Today, we're going to go in depth into our analysis of mining VideoCoin on CPUs versus GPUs. So we've spent a lot of time analyzing what the right way and what right infrastructure is required for VideoCoin. And then we're very excited to share our research results in this presentation. This, again, is a part of our alpha release that you guys saw a couple of days back. And then these series of videos shed some light into the work that we've been doing over the past year over getting VideoCoin into alpha and then beta and production. So I'm going to hand it over to Ram for him to take over the research and analysis he's done. So Ram, do you want to start?
Yes. Let's skip to the next slide. So basically, we want to create a uniform measurement of the mining being done in order to reward it uniformly. So it basically contains three different mining activities. One is the transcoding, the storage, and the other one is network. So basically, it's a challenge to come up with a kind of uniform measure across different platforms, including Google Cloud instances and hardware accelerators. To start with, we came up with a definition of watt that can be tied to the amount of work being done by the miner, and come up with associated payments. The watt we defined it as basically decoding and encoding H.264. So basically, the definition contains a tons rating, not resolution change. That you want to use it as a basis and calculate the wattage required for when there is a scaling operation, basically changing the resolution and encode again, as well as format change. If the source format is H.264 and destination is H.265, that requires a kind of scaling on the base wattage that we define. So we continue to improve it, but the current measurement is based on a lot of test cases being run on Google Cloud instances as well as Intel QuickSync encoders as well as NVIDIA's GPUs. Let's go to the next slide.
Yeah, so I think just a little bit more color on what Ram was saying here is like, if you go back to our white paper, we have a unit of processing defined in it called as watt. A watt is like Ethereum has gas, VideoCoin has wattage. And a wattage in VideoCoin network is way more complex than just gas processing in Ethereum, because in Ethereum, the only gas that you pay for is compute on the EVM. However, in VideoCoin, there is processing power that is required for transcoding. There's processing power that is required for storage and internet bandwidth. And on top of this, there's also transaction wattage. So wattage, we've split a wattage into several sub-components. And the watt, the omega itself, is a weighted average of all of these CPU time, GPU time, storage, and internet bandwidth. And the proc wattage is like we call that unified metric as a proc wattage, which is processing wattage. And then we have another unit called TX wattage, which is transaction wattage. So like a weighted average of all of these is what forms an omega, which is overall wattage. And the research here Ram has done in establishing what a transcore wattage needs to be. He's starting off by defining what a watt means. It's kind of a tongue twister there, what a watt means. So he's trying to define what a watt is and then going on from there. So like in this case, you can see he's defining a watt as decoding or encoding, decoding and encoding X number of macro blocks at a different, at a set profile and at a set bitrate. So this helps us establish what the processing power of a particular compute node is. From there onwards, it helps us establish more data around it. So this brings us to the next slide, which Ram was talking about. So like, Ram, do you want to go now?
Yes. we did a lot of measurements on Google Cloud instances, ranging from all the way to single core to up to 64 cores. Uh, we used FFmpeg to measure the transcode capabilities and translate it into a wattage as per the previous definition. Instead of finding a linear relation between the wattage and the cores, because the way the transporters use multi-threading distributed on multiple cores, there may be a non-linearity. In this graph, we try to show uh, the wattage that can be attributed to different Google instances containing various cores all the way from 1 core to 64 cores.
Yeah. So again, like just a little bit more color here is all of this data measurement that we're doing is representative of how and where our miners would run VideoCoin to provide video infrastructure, right? Like there are different types of CPU cores available and different types of CPU GPU combinations available. The easiest way for us to benchmark all of these is to use existing public cloud infrastructure. And that's what we've done here and establish what the maximum wattage availability is for each type of nodes. So 4 core, 8 core, 16 core, and 32 core. And at 32 core, it's getting like a wattage of 1, and which is kind of a little bit non-linear in terms of how 8 cores and 16 cores deal with multi-threading. That's what Ram was talking about here.
As part of the measurements, we also try to map how many frames per second a machine instance can produce. Basically, this allows a mapping between wattage and FPS performance.
Yeah, this is pretty straightforward. As you can see, like with more cores, the number of FPS increases. Again, it's not linear because multi-threading is different in different CPU cores, and that is a big challenge for us as we're establishing proper wattage metrics for every different type of computer.
Again, it is a different metrics compared to the FPS. Instead of identifying the resolution, Ultra HD, HD, 720p like that, we try to map between the macro block transcoding capability of the instance of both H.264 and H.265 on one particular instance of 32 core.
Yep. So again, like this is, you see that there's like an inverse correlation between this graph and the previous one. It's obviously because as the number of frames per second increases, the number of macro blocks that you can process also increases. So that's the inverse correlation that you guys see here. Yeah, and then that's split between two different codecs here. Right, Ram? Did I get that right?
The top one is H.264 and
the bottom one is H.265, correct. Yep, moving on.
We also extended the study to Intel QuickSync on their some of the latest i7 processors, as well as NVIDIA's GPUs associated with Google instances. For the Xeon instances on the cloud, you can find a kind of uniformity between wattage and its transport mining capabilities. But in case of QuickSync, it uses a fixed function encoder as well as decoders. That basically bumps up its wattage capability or its transport mining capability compared to the cores available there. Similar thing with GPUs associated with Google Cloud instance. We took a Google Cloud instance of 8-core machine and run tests to see the transport performance of NVIDIA's Tesla P100. They have some kind of acceleration for H265. So as part of it, the format scaling that is applicable for Google Cloud instances may not be applicable for the GPU because there is a kind of fine-tuning the performance towards H265. That is what we noted here. So the accelerator seems to perform uh, better at H265 compared to H264. That is because of the tune. That is what we noted here.
Yeah, so I think this is one of the most important findings that we have for over our research, and this is something that we've been excited about for a long time. Is if you see the first 4 entries here in this graph, they're all Xeon CPUs. So Xeons are the highest end server CPUs that Intel ships. And as you see, even in the best one, even at 32 cores, the wattage that you have available is just 1 based on, like the way we defined wattage in the previous slides. Or as you can see on a quick sync machine, which is just a Core i7, which is a consumer grade CPU. It's not even a server grade CPU. On a consumer grade CPU, you see that it is twice the performance of even on the best highest end Xeon CPU. And it even gets, and compared to a GPU like NVIDIA that has a fixed function core, it is 10 times better than what a Xeon CPU can do on the same Google Cloud instance. So this is something very powerful that we are leveraging for VideoCoin, where we're using the QuickSync is basically end consumer. QuickSync is Intel's fixed function video pipe. We'll put links to QuickSync in the blog post accompanying this video. But QuickSync is basically the interface to the fixed function video encoders and decoders available on Intel CPUs. Not too many people and not too many products use this part of the CPU pipe, but we want to use that for VideoCoin mining. And as you can see, even on a consumer grade CPU, the wattage available through QuickSync is several folds higher than what you would get on a high-end Xeon CPU. So this is the most exciting finding for us. And then this is something that we were planning to use for a long time. And these performance benchmarks and metrics set in stone are a path forward in terms of using QuickSync and NVIDIA GPU. So as of in terms of whether we can use QuickSync or NVIDIA for Alpha itself, presently, yes, we can. Because of the way we are using QuickSync through FFmpeg, we can replace, and the way, because of the way VideoCoin architecture is in such a way that we can plug and play encoders, we can actually remove software-based encoders and replace it with QuickSync and use QuickSync in our present alpha demos. So this is super exciting for us, and we'll write an additional blog post to go along with, so you can check out all the data that we've collected. And so we will, all our mining research, we'll keep publishing it on our blogs, and then, but this is a great place for us to, this is a great milestone for us to accompany Alpha, where we established what the wattage availability is of high-end cloud instances and consumer grade CPUs, and as we always maintained, the end consumer CPUs are like performing better than high-end Xeon CPUs, because the consumer grade ones, which have QuickSync and the NVIDIA's NVINC, have fixed function video pipe. So like, that's also why the NVIDIA Tesla product is also very exciting for us, because they expose the similar consumer grade functionality in server hardware. So as this Tesla chip proliferates more in data centers, and more companies start offering Tesla-based cloud computing instances, those can be used for mining VideoCoin as well. So that's about it for us. Ram, do you have any concluding remarks?
Yeah, the results seems to be pretty interesting, particularly supporting hardware accelerators. And they are also trying to come up with measurements for the network throughput and storage wattage.
Great. All right. This is the summary of our research into mining VideoCoin and CPUs and GPUs. Stay tuned for our stay tuned for more videos on our channel and as part of our alpha release. Thank you.